In this lesson we're going to look at supporting forces using the principle of moments, and to do that we've got a setup here where we've got a light beam supporting a load here in blue and supported by two cables or two ropes. And before we start, when we refer to the beam as a light beam, the word light in this situation really means that we're ignoring the mass of the beam, so we ignore its weight. So we're treating the beam as if it had no weight, and so this word is often used in exam questions. So basically what it means is you don't need to worry about the weight of the beam or the plank or whatever. Okay, so what we're going to say first of all is that in a situation like this, the tensions in each of these cables, okay, we refer to A and B. Okay, so the tensions A and tension B would not necessarily be the same. They would depend upon the position of the load on the beam. Yes, they will be the same if the load is exactly in the middle, but if the load is shifted either to the left or the right, then the tensions TA and TB will be different. Okay, so what we're saying is that the weight being supported in this setup is not shared equally between the two ropes or cables as you might possibly intuitively think. Okay, so we want to sort of purge that idea from your head, and that the tensions TA and TB will depend upon the position of this load, assuming that this is a light beam. So we'll do that in this lesson. In the next lesson we're going to consider the situation where the beam does have a weight. Okay, so we'll complicate the setup a little bit more. So then, let's just imagine that this distance here is 3 meters and this one 6 meters, that the load it's supporting is 600 newtons, and what we've got to do is calculate the tensions TA and TB. How are we going to do that? Well, we're going to apply the principle of moment. So first of all, we're going to imagine that the beam and the load are able to rotate around this point here. So this acts as a pivot point, and we'll calculate the moments around pivot point A, and then we'll do the same for pivot point B. Now the plank, load and supporting cables are in equilibrium. Nothing's moving, so everything is balanced. So first of all, by considering the rotation around point A, well, we've got a clockwise moment produced by the 600 Newton weight acting in this direction. So we can say that 3 times 600 must be balanced by the anti-clockwise rotation around point A produced by tension B at a distance of 3 plus 6 equals 9 meters from the pivot point. So we say 3 times 600 is equal to 9 times TB. Well, that tells us that TB is equal to 3 times 600 divided by 9. That's 1/3 of 600, which is equal to 200 newtons. Now then, we can repeat the procedure for point B. We can say that point B is now the pivot, and we can calculate the moments around point B. So doing that, we have an anti-clockwise rotation around point B produced by the weight 600 newtons acting this way. So we've got 6 times 600, and that will be balanced by a clockwise moment produced by the tension TE acting at a distance of 3 plus 6 meters from the pivot point B. So that's equal to 9 times TA, which will give us TA is equal to 6 divided by 9 times 600, which is 400 newtons. So you'll see straight away that you didn't actually need to do that calculation, because what we're calculating here are forces that are acting in the vertical direction. We've got a 600 Newton force acting that way, and we've got two tensions which are acting in the opposite direction. And clearly, if this setup is in equilibrium, then TA plus TB must be equal to the weight acting downwards. So having first calculated TB to be 200 newtons, then all we really need to do is plug it into this equation. So we would have TA plus 200 newtons is equal to 600 newtons. Again, that would give us that TA is equal to 400 newtons, which is what we'd expect. Okay, so in the next lesson we'll consider a setup where our beam has got a weight